For years we've been hearing these, frankly, staggering numbers about quantum speed. But today feels different. There's proof. A quantum computer running an algorithm, a verifiable one, 13,000 times faster than the best classical supercomputers. Well, it's not just fast, it's trustworthy.
Exactly. And that shift from just speed to verifiable precision, that's huge. Today, we're digging into Google's new quantum echoes algorithm. It ran on their Willow chip, and it really does mark the first verifiable quantum advantage demonstrated on actual hardware. It's built on some pretty deep physics, too.
Okay, hold on. Previous claims, like back in 2019, they got pushback, right? People said, well, how do you even check that? Or that it'd take forever classically. So what's different now? Why is verifiable suddenly the magic word here?
That's a really important question. It shows how the field is maturing. Verifiable means the result isn't just some complex output spat out by the machine. No, it's repeatable. You can run it again, get the same answer. And crucially, it can be cross-benchmarked on other similar quantum computers. It confirms the precision alongside the complexity. They manage this partly because of their error suppression work from 2024.
Oh, okay.
So you get the quantum speed, but with, let's say, a kind of classical assurance check built in.
Got it. Okay, so let's talk about the name quantum echoes. What's the science, this OTOC thing you mentioned?
Right, OTOC. It stands for Out-of-Time-Order Correlator. That's the physics tool behind it all. Basically, OTOC helps describe how quantum information spreads out, sometimes called information scrambling. Think of it like trying to measure the quantum butterfly effect. How a tiny, tiny change can ripple out and affect the whole system.
I get the butterfly analogy, but how do you actually measure an echo like that on a chip? What are they physically doing?
It's actually quite clever. It involves playing with time evolution. So they send a signal forward through the qubits, standard enough.
Okay.
Then they deliberately perturb just one single qubit. That's the butterfly's flutter.
Right.
But here's the key part. They then precisely reverse the quantum evolution of the whole system, run the clock backwards, so to speak. In quantum mechanics, that's something you can actually do.
Right.
It's a known structure, reminds me a bit of the Loschmidt echo.
They run time backward.
Yeah.
And that creates the echo. How?
Exactly. By running it backward, they're essentially listening for the signal to reform. When the reverse state overlaps perfectly with the original undisturbed state, that overlap isn't faint. It gets amplified. It's called constructive interference, like two waves hitting each other just right and making a much bigger wave.
Oh.
And the pattern of that amplified signal, that echo, tells them exactly how that initial poke, that disturbance, spread through the chip. It's a diagnostic tool we didn't really have before.
Okay, so beyond tuning the hardware, what does this mean for actual problems, real world stuff? This sounds like it could be huge.
Oh, absolutely. The immediate thinking goes towards medicine, materials science. They actually did a proof of principle experiment on the Willow chip using this. You used it as a kind of molecular ruler.
A molecular ruler. You mentioned studying molecules up to 28 atoms. How does that compare to something like NMR? Isn't that the standard?
It is the standard, nuclear magnetic resonance. But NMR has limits, especially with complex dynamics, and you usually need lots of molecules. This quantum technique is different. The results they got for those 28 atom molecules, they match the NMR data, sure.
Yeah.
But they also revealed details about the internal dynamics, how things move inside the molecule that you just can't typically get from classical NMR, information that was basically hidden before.
Wow. So it's like a quantum microscope almost, a quantumscope.
Sure.
Is 28 atoms the limit for now? How fast can they push that number up?
Well, 28 atoms was the demonstration, the proof it works. But yeah, the goal now is scaling it up to model bigger things accurately. Complex proteins for drug discovery, maybe new materials for batteries or polymers. Being able to measure these things we couldn't see before. That could really accelerate finding new drugs, seeing exactly how they bind, or designing better materials from the ground up.
This deep dive is sponsored by Embersilk.com. Embersilk is the answer for all your AI education and integration needs.
And, thinking bigger picture, this whole verifiable advantage thing, it really feeds into the next major goal for the whole field, which is achieving a stable, long-lived logical qubit. That's the bedrock for fault-tolerant quantum computing. And it poses a really interesting question now. How does this demonstrated need for both speed and that verified precision?
Oh.
How does that shift the roadmap? Will we see more focus on quality, on precision, maybe over just raw speed claims?
That is definitely a critical point for you, our listener, to think about as this technology races forward. If you enjoyed this deep dive, please do subscribe and give us that 5-star review. It genuinely helps us out a lot. We'll catch you next time for another deep dive.